Hey everyone, welcome back to Intelligent Machines. In the last video, we discussed how to use diffusion model to generate images from given class label, where we introduced a new parameter called class label to our unit or the diffusion model, so that during inference, when we provide class label, the model denoises random noise to generate an image from that class. But so far, we have not used images yet. We are just working on 2D points because it's very important to understand the concept of diffusion before we start applying it. So in this video, we are finally going to see how to implement the diffusion process for images. We're going to focus particularly on the MNIST data. So what is the main difference between points and images? In the previous videos, we used 2D points. Each point Each point here has an X and Y coordinate, but for images, it is much higher dimension. For example, let's say if this image is 256 height, 256 width, and three color channels, that means there are number of dimensions becomes 256 into 256 into 3, which is pretty huge. So the only real change is that how diffusion happens in higher dimensional space. Rest everything else remains the same. And in this video, our focus is going to be on the MNIST data. We'll try to generate digits based on the class label. For example, if we say, let's say, in the diffusion model, we pass a label 1, then it should generate the handwritten digit 1. So these are some results here. These are generated by the diffusion model that we are going to create today. I'm going to divide this video into two parts. In the first part, I'm going to implement everything from scratch using pure Pytorch, just so that we have an understanding of how it works, but that is not practical all the time. What we would like to do is we would like to take advantage of this diffusers library. All codes are available on my GitHub and the link is in the description below. Initially, we import all the necessary libraries, and here is a small transformation that we define. So by default, these MNIST images are in the range of 0 to 255. When we call torch vision.transform.toTensor, this is toTensor method, it converts 0 to 255 images into 0 to 1, basically divides by 255. And then we normalize that. Then we transform that into tensor with values with mean 0 and standard deviation 1. Once we apply this transformation, we pass this transformation here, we are all set with the data preprocessing. If we print one element from the dataset, we get two things: the image tensor, this one, and the corresponding label, that what digit this one represents. And if I plot that using plt.imshow, you see this is the fifth digit. Now to visualize multiple such samples, we can use a small helper. So this one. And the helper comes from torchvision.utils.makeGrid. So what happens here is instead of one image, we can plot, let's say 64 images directly, just like that. And for that, I'm using the data loader. So what the data loader does is it takes the dataset and batches them, batches on a size of 64. So at once we have 64 images and 64 labels. If you see x.shape, there are 64 batches, one channel because it's an grayscale image, 28 cross 28, the height and width. And this usually we are doing this denormalization, you can say. We are doing this because right now our images are in the range of -1 to 1. It will be better if we convert them back into 0 to 1. So for that, we do this transformation to cancel this initial transformation that we do during the plotting part, especially. Next, we'll go to the forward diffusion process. As we already know, in diffusion, we keep on adding noise step by step to the image. We define the beta values, alpha and alpha bar. Alpha bar is cumulative product of all the alphas and allows us to directly move from the original image to any noisy version of it in one step instead of adding noise repeatedly. This gives us a quick way to simulate the noise process at any time step. And now we are doing this forward process on a single batch of data. So for example, what will happen? We'll keep on adding noise gradually using the scheduler that we just created. This is the forward diffusion process, the images of the digit, and add a noise to it using this scheduler alpha bar. And that's how we get the noised version. And as time progresses, we get more noise. We keep on adding more and more noise, and finally we are ended up with almost random noise. Now comes the most important part, the unit model. This is where things change compared to our previous example with just 2D points. For images, we use convolution layer instead of simple linear layer. Here is a basic idea. We take the input image X, pass it through the sequence of convolution layers. These are all the convolution layer. And inside the convolution layer, we also use group normalization and silo activation. We also add two important parameters, time step embedding to let the model know that what time it is denoising at, and also the class embedding to let the model know that for which class we are denoising, so that we end up with a particular class. The green ones you see are the downsampling layers. The blue ones you see are upsampling layers. The yellow are the residual connections, and the final layer predicts the noise to be removed from the given noisy input. Each input goes through several layers of encoding. This is the encoding part, and then several steps of decoding. Similar to an autoencoder structure, during encoding part, we are keep on downsampling them. For example, the 28 cross 28 image downsamples to 14 cross 14 after this, and then again downsamples, and after that we keep on upsampling them. So here you see upsample layers. Now let's see how we create this one in Pytorch. We will create a new class, myUnit, which will be based on this nn module. And in the init method, we are initializing the down layers, the up layers, the time embedding, and class embedding. There are also two small part. One is downscale, like when during the encoding part, we downscale our images to a smaller dimension. And in upscale, we upscale the same one to a larger dimension. And this is our forward method. One important thing in forward method is how we combine the time embedding and class embedding with the convolution layer, because the time embedding is going to have, it's a one dimensional, it's a linear layer. So even though we pass, let's say time embedding, we pass the timestamp, let's say 10, then it will convert it into a 32 dimensional vector, nothing else. But how we will add this 32 dimensional vector to our convolution layer? For that, let's go back here. So we are not adding, we're adding after first layer of convolution. So our input will have 28 cross 28 cross 3 channel. And after convolution, it will have, let's say, 28 cross 28 cross 32 channels. So now we have 32 channels, and this embedding is also has 32 dimensions. So add them along that dimension, that particular dimension, both class embedding and time embedding. They have 32 dimensional vector, and we add that to this up to the activation after this first convolution. That's what we do here, and this is the only important part. So here, so first we go through the down layer, and after the first layer, that means when I equal to 0, the first layer, we add the timestamp embedding and class embedding there. There are many other ways to do it, but this is the way I choose to go along with. Instead of right now, I'm using linear layer. Many people use time positional embedding or sinusoidal embedding for both the timestamp embedding and class embedding as well. So that is one thing to note. But in this time, I'm keeping it simple and just using a learnable parameter. So in the downsampling layer, we keep on saving our residual connections to this list, and then during the upsampling layer, we keep on adding the residual connections to our activations, and that's basically all of our unit. Here is an instance of the unit that I created, the input, the timestamp embedding, and the class embedding. I pass them, and the output shape you see is same as the input shape. This basically works as an autoencoder, but it predicts the noise that needs to be removed. So we'll come to this generate image method later. First let's look at the training method. It's not very long, very simple. First we define the loss function and the optimizer here, and we are doing it for 50 epochs. For each batch in train data loader, we are getting the image X and the label Y. We are moving our image to the device or GPU, and initially we are putting our unit model in the training mode. Then we are sampling a random timestamp between 0 to t. Here it's t is I think 1000. Sample a random noise which has the same shape as x, and this is the forward diffusion process. After that, we get the x noised. Then we pass the x noise to the model, the timestamp and the corresponding label, and we get the predicted noise. Then we do the loss function is calculated between the predicted noise and the true noise. After that, we do the backpropagation, we optimize, we update the weights, and we clear the gradients. And after every 5 epoch, we generate image. What is this generate image function? This is useful to generate some images after a few epoch to see how our generation is progressing. So let's look at it. So what we are doing is we're sampling a random noise of shape 10 cross 1 cross 28 cross 28, a given label, because we want to generate labeled data. So we want it to pass 0 to 9. They are the label according to which we want to denoise. First, put our unit in the evaluation mode. Then this is our denoising loop. We're going through the timestamp, but in reverse direction right now. We start from 1000, then 999, then 998, so on. At each step, the model predicts how much noise that needs to be removed from this input. And once you get the predicted noise, this is the denoising step. This is the denoising step from the DDPM paper, which we have been discussed in previous and last to the previous video. And this goes in a loop. This XT goes in a loop until we go through the entire timestamp. And then we plot that. So what is happening? So you see after, let's say, 5 epoch, this is how it looks. After 10 epoch, this is how it looks. And so on and so forth until I think, yeah. And so here it start kind of 0, 1, 2, not very accurate, but it start learning something. Yeah, I think this is the final epoch I stopped at. After, even though 50 epochs, the result may not look very perfect, but you still start to see some recognizable digits, and they are also kind of faithful to the label we are giving. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a great starting point for understanding how diffusion model generate images from noise. In the next video, we'll take the same idea, but in the next video, we are going to see how we can use diffusers library to do that. That way we can use pre-built components for scheduler, models, and pipelines without writing everything from scratch. So stay tuned for that. If you find this helpful, please like the video, subscribe to Intelligent Machines, and share it with your friends who are learning about diffusion model. See you in the next one.